Let's talk now about hydroboration. Hydroboration achieves the same thing as the previous ones did. That is, we get the hydration and the hydroxymercuration, in that we get an OH attached to wherever double bond was. But the hydroboration does it in a different way. The addition we get with hydroboration is often called anti-Markovnikov addition, because if you look closely, you see where the OH ends up on the double bond. It actually ends up on the least substituted carbon. Well, let's see if we can explain why that is. Alright, so we've got a double bond compound here. And what we're going to do is we're going to add B2H6 and then H2O2 and OH minus. And what's going to happen is the product we're going to get is not the one we'd expect to get for a Markovnikov addition. Markovnikov addition would have the OH on the most substituted carbon. This puts the OH up here. Alright, let's see why that is. If you've got B2H6, B2H6 is called diborane, and it has this kind of structure. It's called a dimer because it's really just two BH3s joined together, and it splits pretty easily into two BH3s, because if you look at these hydrogens here, they've each got one and a little bit bond here, and usually hydrogens like to have just one bond, so this splits up fairly easily into borane, and that's going to be our effective reagent here. So we'll get two boranes. Now if you look at borane, you'll remember that boron is electropositive and is going to actually be less electronegative than hydrogen is. So the electrons in the BH bond will be closer to the delta minus, so will be closer to the hydrogen than they will be to the boron. So when we look at the reaction, we can look at it in two ways. We can either split the borane up into H minus and BH2 plus, or we can leave them together. First of all, I'll split them up and show you the effect of that. So just like H plus, the BH2 plus will react with a double bond, and what we expect to happen is exactly what does happen. The plus goes where it's supposed to go. And it goes on the more substituted of the two carbons, so the plus ends up there. The H minus can't help but react with the plus, and that leaves the BH2 on the least substituted carbon. Now the purpose of the H2O2 and the OH minus is to take this BH2 and convert it into the alcohol. Just do that here. And I don't really want you to worry about how that happens. Just know that is its purpose. It's an oxidizing agent, and it's in base, and it will take the BH2 and turn it into an OH. So now you can see how it happens, how the B2H6 ends up causing what looks to be an anti-Markovnikov addition. Let's do this another way now. Now I know that in the way I explained it earlier, I split up the BH2 a BH3 into BH2 plus and H minus, but in reality they remain bonded throughout the course of the reaction. So explaining what I did the way I did before, we know that that's delta plus and we know that's delta minus. So what happens is the electrons actually go this way, with the electrons from the bond being attracted to the B, so that the partial positive charge ends up on this C down here. But it is a concerted process, so that's what we end up with. Now on the test, I don't mind if you show it this way or you show it the way that I showed it earlier. I like the way I showed it earlier only because it really does show why the positive charge ends up here. The H minus ends up being attracted to the positive charge, and then the BH2 ends up going on the least substituted of those carbon atoms. Then the same thing can happen. We take the H2O2 and the OH minus and we can convert that into an alcohol.